At this time, we'll be studying Heat Pump Diagnostic Module 5 and 6. And remember, team, if this was a live session, this would be a recorded session if it was a live session. But today we're going to be doing Heat Pump Diagnostic Module 5 and 6 as a recorded session only. So welcome to the Heat Pump program. We're going to be talking about some key things today as follows. We're going to overview the refrigeration cycle for cooling and heating modes of operation. We're going to review the saturation pressure temperature chart, and we'll have some practice session together. We'll talk about superheat and subcooling and the condition that they relate to, specifically superheat in the cooling coil and subcooling in the warm coil today. So at this time, let's go ahead and review the heat pump cycle for the cooling mode of operation. You'll notice right in the middle of the screen, you'll have a suction gauge and a discharge gauge, and those will both be displayed as pounds per square inch gauge. You'll notice on the left side, the suction gauge has got a blue outer ring indicating it's a low pressure, and on the right-hand side, the right gauge has got a red ring indicating it's high pressure discharge. Now also, as you take a look at those gauges, you'll notice that they have a white background. If you have a white background on any of our service calls throughout the rest of the day, you'll automatically know it's an R22 call. If it has a rose-colored or a pink background, you'll know that those gauges are actually indicating a 410A service call. So, starting at the compressor, we see that we have a hot gas line from the compressor going to a single line on the reversing valve. And in the cooling mode of operation, that hot gas from the compressor is diverted to the outdoor coil, which is acting like a condenser in the cooling mode. We then condense that hot gas from the compressor into a liquid. We pass that liquid through a biflow metering circuit, specifically a biflow TXV. Now remember, team, whenever we're talking about a TXV, we're also talking the same component is also known as an expansion valve. So you'll hear that terminology interchangeable today. TXV and expansion valve are the same thing. So again, we take that hot gas from the compressor to the outdoor coil in the cooling mode of operation, and we condense that hot gas into a liquid. We then pass that liquid through a biflow metering device, a TXV in this case. We then pass it down through a biflow filter dryer and then down the liquid line. You'll notice there's some arrows around the refrigeration circuit indicating the flow of the refrigerant. So we see liquid is flowing from left to right in this example, from the outdoor coil to the indoor coil in the cooling mode of operation. So the liquid will then pass down to a biflow TXV on the indoor coil where it's going to be metering refrigerant into the indoor coil. Now remember, team, in the cooling mode of operation, the indoor coil is acting like an evaporator, and we have it color-coded blue, indicating it's cool or cold. From the indoor coil, it's acting like an evaporator in the cooling mode. We come down the indoor coil vapor line back to the reversing valve, where we loop through the reversing valve and to the suction of the compressor. Now again, we're going to point out the fact that if the outdoor coil is red, that means it's hot, so we're in the cooling mode. If the indoor coil is blue in this case, that means it's cold. Now when we reverse cycle, we'll see that the indoor coil becomes hot in the heating mode of operation on a heat pump, and the outdoor coil becomes cold in the heating mode on a heat pump. Now team, remember, this is an important concept. A heat pump allows us to heat and cool the conditioned space with the refrigeration cycle. So our next subject here is the heat pump cycle and the heating mode of operation. You'll notice that the arrows are pumping in the opposite direction because we have reversed flow in the coils on the heat pump in the heating mode. So starting out at the compressor, we see hot gas from the compressor goes into the single line on the reversing valve, and now that reversing valve is diverting that hot gas into the indoor coil that's acting like a condenser in the heating mode of operation. That condenser coil on the indoor coil, specifically, the evaporator now is acting like a condenser. We take that hot gas, we condense it into a liquid, and we pass it through the indoor biflow TXV. We then have that liquid coming down the common liquid line through the biflow filter dryer, where it enters the biflow TXV on the outdoor coil in the heating mode of operation. That outdoor TXV then meters refrigerant into the outdoor coil, which is acting like an evaporator in the heating mode, and it's cold. And so the refrigerant boils off in that evaporator, absorbing heat from the outdoor air, and that cool vapor then goes down the outdoor coil vapor line, loops through the reversing valve back to the suction of the compressor. You'll also notice that the gauges have not changed. The suction gauge is on the left-hand side, the discharge gauge is on the right-hand side, and those are both indicating PSIG. Now later on in the program, we're going to activate those gauges, and we're going to activate some temperature probes, but for this part of the session, we just want to make sure everybody understands that the heat pump, in the heating mode of operation, we have refrigerant hot gas going to the indoor coil, and in the cooling mode of operation, we have hot gas going to the outdoor coil on the heat pump. So at this time, team, if you'll please refer to your pressure temperature chart in your handout packet or your workbook, we're going to do some saturation pressure temperature chart practice. Now in this session, we're going to have you, excuse me, we're going to have you looking up pressures and temperature relationship off of your chart. So starting with your 410A pressure temperature chart, you'll find those columns on the right-hand side of your chart. Starting at with the 410A pressure temperature chart, please find 52 PSIG on your 410A chart, and let's take a look at the temperature together. So at 52 PSIG on 410A, we see that the pressure temperature conversion is 3 degrees. The next one at 136 PSIG for 410A is 47 degrees. Now team, it's always important that we understand we have to find the pressure temperature relationship off of this chart. So when we start doing some service calls later on, we're going to have to take a suction pressure and convert it to temperature. We're going to have to take our discharge pressure and convert it to temperature. And this is what this practice is all about at this time. So our next one, 410A, is 269 PSIG. Please convert that to temperature. Good, it should be 89 degrees. The next one is 375 PSIG off the 410A chart. And we see that's 112 degrees Fahrenheit. The final example for 410A in this exercise is 465 pounds of pressure, PSIG, equates to what temperature? Okay, good, 128 degrees. Now, if you'll please refer to the left-hand side of your pressure temperature chart, you're going to notice there's going to be some R22 columns. So let's do it together. So at 38 PSIG for R22, at 38 PSIG, what is the pressure temperature conversion at 38 PSIG? Good, about 16 degrees. Now remember, team, just round up or round down to the nearest value, to the whole value. It's important that we get close, but if we're within a half a degree or even 1 degree, that's close enough for field work. Our next one for R22 is 68 PSIG, so referring to your chart, at 68 PSIG, what is the pressure temperature conversion? Good, 40 degrees. That's an excellent answer. You should have 40 degrees. Let's do another one at 85 PSIG. What's the pressure temperature conversion? 51 degrees. And at 235 PSIG for R22, what's the pressure temperature conversion? The answer is 113 degrees Fahrenheit. And our final example off our pressure temperature chart at 325 PSIG for R22, what's the pressure temperature conversion, please? Good, about 137 degrees. So team, this is important. We need to be able to refer to the pressure temperature chart because some of the things we'll be looking at here shortly in our module will be superheat and subcooling of the evaporator and the condenser coil. And so we have to be able to find pressure and temperature readily and quickly, the pressure temperature conversion, because that's an important key point in finding superheat and subcooling on our evaporator and our condenser coils. So this time, let's talk about superheat and the cooling coil. Now remember, team, the cooling coil can be the indoor coil in the cooling mode of operation on a heat pump, but it can also be the outdoor coil in the heating mode of operation. So one thing we always need to keep in perspective is that superheat always applies to the cooling coil. Now remember, team, there's only 3 conditions the cold coil can ever be in. It can be flooded, there's too much refrigerant in there. It could be starved, there's not enough refrigerant in there to get the job done, or it could be normal. Now please write this down, or make a note of this. Superheat, normal superheat on the cold coil on a heat pump should be about 10 to 15 degrees Fahrenheit superheat in the cooling mode. One more time, normal superheat on the cold coil in the cooling mode of operation should be about 10 to 15 degrees of superheat. In the heating mode of operation, because we're building a lot of ice on the outdoor coil, superheat can vary somewhat in the heating mode of operation on a heat pump. So normal superheat on a heat pump in the cooling mode of operation is 10 to 15, we learned a minute ago. But in the heating mode of operation, normal superheat can range anywhere from about 4 degrees to 15 degrees. So again, we have to kind of swing our superheat value around a little bit in the heating mode of operation on a heat pump, because as we start building ice on the coil outside, that's going to drive the superheat low on that cold coil in the heating mode. So in the heating mode of operation, about 4 to 15 degrees will be considered normal on a heat pump in the heating mode, and about 10 to 15 degrees in the cooling mode will be a good normal parameter. And remember, team, the only condition that a cold coil can ever be in is flooded, there's too much liquid in there, normal, about 10 to 15 in the cooling mode, and about 4 to 15 in the heating mode, or starved, there's not enough refrigerant in there. So as we take a look at superheat, it will always help us figure out the condition of the cold coil. Now please write this down before we start doing some superheat practice one more time. Make a note or two on your page or on your handout. If the superheat is high on the cold coil, that coil is starved. If the superheat is low on the cold coil, that coil is flooded. Normal superheat on a cold coil should run about 10 to 15 degrees in the cooling mode, and as low as 4 degrees to 15 degrees in the heating mode. And again, just double check now, if the superheat is high, the cold coil is starved. If the superheat is low, the coil is flooded. And if the superheat is normal, it'll fall within that range of about 10 to 15 for cooling mode of operation, and about 4 to 15 degrees for heating mode of operation. Now, to calculate superheat, the first thing we're going to do is we're going to convert suction pressure to temperature off of our pressure temperature chart, just like we did in practice a few moments ago. Step number 2, we're going to measure the suction line temperature leaving that cold coil. Step number 3, we'll find the difference in temperature between step number 1 and step number 2, and the difference is our superheat level. And remember, team, by looking at the condition of the coil, flooded, starved, or normal, it will help us determine where the refrigerant is in the refrigeration cycle, and it'll also help us be a better diagnostic technician. So at this time, let's do some superheat practice together. As we refer to our superheat practice sessions on our PowerPoint, let's do some superheat together. And so we'll take this a step at a time. Please have your pressure temperature chart handy as we do some superheat practice on the cold coil. In our example here, we see that we've got a R22 service call because we have a white background on our gauges. You'll also notice that there are some yellow blocks that are displayed throughout the refrigeration circuit. All of those yellow blocks are not filled in because those are along the liquid line, and we'll engage those later when we do diagnostic service calls. So the The yellow temperature blocks that are engaged at this time are the ones along the suction line circuit. And we see that it's 59 degrees along the cool suction vapor line with the heat pump in the cooling mode of operation. We also notice it's an R22 call because our gauges have a white background. Now remember, team, if they had a pink or a rose-colored background, that would mean it's an R410A call, and we'd use the appropriate chart on our pressure temperature chart. So as we take a look at this example here, we see we have 44 pounds of suction pressure, R22. And at 44 pounds of suction pressure, as we refer to the chart, we see that gives us a temperature conversion of about 21 degrees. So as we take a look at 44 pounds of suction pressure and 21 degrees, we then find the difference between 21 degrees, step number 1, that we got off of our chart, and step number 2, the physical line of the suction line temperature in our example. And we see the difference is the difference between 59 degrees suction line temperature and about 21 degrees saturation pressure temperature conversion off the chart. So the difference between 21 and 59 is about 38 degree difference. And so remember, team, we said that if the superheat is high on the cold coil, the coil is starved. If the superheat is low, if it's a low number, the coil is flooded. And normal is about 10 to 15. But in our example, we see that we have over 30 degrees of superheat. 10 to 15 is normal, so the number is high. We have a high superheat number. That means the indoor coil in this example, in the cooling mode of operation, is starved for whatever reason. Now, team, we'll find out what some of those reasons are later. This is just strictly superheat practice right now to make sure everybody understands how superheat will help us find the condition, flooded, starved, or normal, of the cold coil. In this example, we see we have 85 pounds of suction pressure, and we notice we have a pink or rose-colored background on the gauges, so we know it's an R410A call. So at 85 pounds of suction pressure, we see that we have a pressure temperature conversion off of our chart of about 24 degrees, about 24 degrees. The temperature leaving on the cool vapor line from the indoor coil, which is the cold coil in the cooling mode, is 54 degrees. It even goes up to 55 before it enters the reversing valve. So we'll just take the average and just say it's about 55 to 54 degrees. So at 24 pounds, or excuse me, at 24 degree saturation temperature off the chart, remember 85 psig, suction pressure, we convert that to temperature, and that equates to 24 degrees. So the temperature leaving the cold coil in the cooling mode on the indoor coil is 54 degrees. The difference between 54 and 24 is about 30 degrees of superheat again. And we found out earlier, and we refreshed our memory earlier, that 10 to 15 is normal, but we have a high superheat value. So a high superheat always means the cold coil is starved. And so again, in this example, this 410A example, we have a starved cold coil. In our next example, we see we have 152 pounds of suction pressure. And 152 pounds of suction pressure for 410A, we have pink or rose-colored background on the gauges. At 152 pounds of suction pressure, we have 54 degree pressure temperature conversion. Well, in this example, we see that we have 55 degree temperature of the suction line leaving the cold coil. That indoor coil vapor line is 55 to 57 degrees with an average of about 56. So with a pressure temperature conversion of 152 pounds of pressure and a 54 degree temperature conversion, we see we only have about 2 to 3 degrees of superheat. Now remember, team, if the superheat is low, as it is in this example, the coil is flooded. So we have a flooded coil for whatever reason in this example. Now in this example, we see that we have a R410A call, but we have switched modes from heating to cooling mode. But that's okay. Remember, team, superheat always applies to the cold coil. So in this example, we see the outdoor coil is cold because we're in the heating mode of operation, but superheat still applies. So let's do this example together. At 88 pounds of suction pressure for 410A, we see that we have a temperature conversion of about 25 degrees, about 25 degrees. However, the temperature of the physical suction line, the outdoor coil vapor line coming off the outdoor coil, is 36 degrees. So the difference between 36 degrees and 25 degrees is about 11 degrees of superheat, which falls within a normal range. Remember, team, in the heating mode, there's a much broader range on superheat because the outdoor coil can start to ice up under cold conditions. So about 4 to 15 would be considered normal in the heating mode of operation. And so in our example, we have 11 degrees, approximately 11 degrees of superheat. The outdoor coil in this example would be considered normal. Okay, at this time, let's go ahead and talk about subcooling in the warm coil. And remember, team, if we can find coil condition, flooded, starved, or normal, on the outdoor coil and the indoor coil, in any mode of operation, it makes us a better troubleshooter. And we'll be tying this all together into a big diagnostic picture when we start getting into Module 6. So this time, let's talk about subcooling in the warm coil. Remember, team, subcooling always applies to the warm coil. It doesn't matter if the warm coil is outside. In the example, in the cooling mode of operation, the outdoor coil is the warm coil. And in the heating mode of operation, the indoor coil is the warm coil. Now remember, team, subcooling always applies to the warm coil, and subcooling will also tell us the condition of the coil. So please write this down or make a note of this. There's only 3 conditions the warm coil can ever be in. Flooded, there's too much liquid in the coil. Starved, there's not enough liquid in the coil. Normal, a normal subcooling level will be about 10 to 15 degrees in the cooling mode. However, because of the physical size difference of the indoor and outdoor coil on a heat pump, the subcooling in the heating mode can go as high as 25 degrees because of the physical size difference. So again, normal subcooling in the cooling mode of operation on a heat pump with properly sized equipment should be about 10 to 15 degrees of subcooling in the cooling mode. But in the heating mode of operation, normal subcooling can go anywhere between 15 to 25 degrees because of the physical size differences of the coils. So in the heating mode of operation, we're going to see much higher subcooling levels. That's normal. So subcooling always tells us the condition of the warm coil. If the subcooling is high, the coil is flooded. If the subcooling is low, the coil is starved. If the subcooling is about 10 to 15 degrees in the cooling mode, we'll consider that normal. If the subcooling is about 15 to 25 degrees in the heating mode, we'll consider that normal. Now remember, team, subcooling tells us the condition of the warm coil, flooded, starved, or normal. If the subcooling is high, the coil is flooded full of liquid. If the subcooling is low, the coil is empty of liquid. If the subcooling in the cooling mode is about 10 to 15 degrees, we'll consider that normal. If the subcooling is about 15 to 25 degrees in the heating mode, we'll consider that normal. So let's talk about how to calculate subcooling at this time. So step number 1, we're going to convert our liquid pressure or our discharge pressure in our example. They're essentially going to be the same. So liquid pressure or discharge pressure we convert to temperature off of our pressure temperature chart. Step number 2, we clamp on our temperature probe and we physically measure the temperature of the liquid line leaving the warm coil. Step number 3, we find the difference between those two temperatures, and the difference is our subcooling level. Now remember, team, if the subcooling is high, the coil is flooded full of liquid. If the subcooling number is low, the coil is starved. If the subcooling is about 10 to 15 degrees in the cooling mode, we'll consider that normal. If it's about 15 to 25 degrees in the heating mode, we'll consider that normal. So this time, let's go ahead and do some subcooling practice. Have your pressure temperature chart handy as we do the subcooling practice on the warm coil. So in our example here on the R22 screen, we see that we're looking at the high side pressure now, or the discharge pressure. So in our example, we have 297 pounds of pressure on the discharge gauge that we're looking at on this particular service call, or this example. Now, team, you'll notice that there's white background on the gauges. Excuse me, that means this is an R22 service call. In addition, you'll also notice that we've deactivated the temperature blocks on the suction line or the vapor line, and we have activated the ones on the liquid line. So as we take a look at looking at subcooling, our step number 1, we're going to take 297 pounds of pressure, and this is an R22 call, so at 297 pounds of pressure, we see we have a pressure temperature conversion of 130 degrees. Step number 2, we see that we have a 99 degree liquid line temperature leaving the warm coil. So the difference between 130 and 99 is about 31 degrees. Now remember, team, in the cooling mode of operation, we're looking for about 10 to 15 degrees of subcooling in the cooling mode of operation, which we're in. So we should have 10 to 15, but we have 31, so our subcooling number is high. So in our example, we have too much liquid in the outdoor coil for whatever reason. Now remember, team, we'll find out what those reasons are later. Right now, we're just looking at subcooling in a practice session. So our subcooling is high in this example. That tells us that the warm coil is flooded. In our next example, we see we have a refrigeration circuit. We have a heat pump. We're still in the cooling mode of operation, but it's a 410A heat pump. We see that we've changed the color of the background of our gauges. And in this example, we have 540 pounds of pressure. Well, at 540 pounds of pressure on our 410A pressure temperature chart, we see that at 540 pounds of pressure, we have about 140 degree temperature. So the difference between 140 degree temperature and 106 degree liquid line temperature, the difference is about 34 degrees. So in our example here, we have 34 degrees subcooling on the warm coil, which is high. That tells us that this coil, for whatever reason, is flooded. In our next example, we see we have a 410A call. We have pink or rose-colored background on the gauges, and we have 401 pounds of pressure for 410A. At 401 pounds of pressure, we see that we have a pressure temperature conversion of about 117 degrees off of the chart. We also notice at this point we have 107 degree liquid line temperature, and the difference between 107 and 117 that we got off the pressure temperature chart is 10 degrees of subcooling. In this example, our subcooling level should be between 10 to 15 degrees, and we're running about 10 to 11 degrees subcooling. In this example, our subcooling on the warm coil is normal. In our next example, we see we're still in the cooling mode of operation, and it is a 410A call. So let's take a look and find the subcooling on this call together. At 323 pounds of pressure off our 410A chart, we see that we have a pressure temperature conversion of about 101 degrees, about 101. However, our liquid line temperature in this example is 100 degrees, and that's only a 1 degree difference. And so our normal subcooling level on the warm coil in the cooling mode should be about 10 to 15 degrees. However, we see that we have a 1 degree temperature difference on our subcooling, and that tells us this coil is starved. It does not have enough refrigerant in it. Our subcooling is low. We have a starved warm coil. In this example, we see we have an R22 service call. We have a white color on the background, and we also notice on our gauges they're not only an R22 call, but we have 192 pounds of pressure on the discharge gauge. Now, team, you'll also notice that we've switched into the heating mode of operation. In other words, the outdoor coil is the cold coil in the heating mode, and the indoor coil is the warm coil in the heating mode of operation. So remember, team, in the heating mode of operation, it's not unusual to see subcooling on the warm indoor coil in the heating mode to be anywhere between about 15 to 25 degrees of Fahrenheit. That would be a normal range. The subcooling is much higher in the heating mode of operation because the indoor coil is full of refrigerant and it's a much smaller coil than the outdoor coil. So subcooling values will be higher on a heat pump in the heating mode. So let's do this example together. At 192 pounds of pressure for a R22 service call, we see that at 192 it's about 98 degrees. About 98 degree is a liquid pressure temperature conversion off of our R22 chart. So at 192 pounds of pressure, we have about a 98 degree pressure temperature conversion. Now we notice that the liquid line leaving the indoor coil is 96 degrees. Excuse me. And in our example, we only have 2 degrees of subcooling. The indoor coil is empty of liquid for whatever reason. So at this time, team, we've talked about superheat and subcooling. We've reviewed that. We've looked at our pressure temperature chart in Module 5. And so now we're going to continue with Heat Pump Diagnostic Module number 6. And we'd like to welcome you to that program as well. So this afternoon we're going to be talking about superheat and subcooling as well. Just as a quick review, we're going to review the Diagnostic System Problems page in your handout, and then we're going to tie it all together with some interactive service calls and practice sessions as we round out this program with session number 6 or module number 6. So again, reviewing superheat and the cold coil. To find superheat, we're going to convert our suction pressure to temperature. We'll then measure the suction line temperature and find the difference, and the difference will be our superheat level. Now remember, team, on superheat, if the superheat is high, the cold coil is starved. If the superheat is low, the cold coil is flooded. If the superheat is about 10 to 15 degrees in the cooling mode of operation, we'll consider that normal. And anywhere between about 4 to 15 degrees in the heating mode of operation will be considered a normal range for superheat on the cold coil. And as a quick reminder, let's do one real quick. At 85 pounds of suction pressure on our 410A unit right here, we see that 85 pounds of suction pressure is equal to about 24 degrees on the 410A chart. However, the difference between 24 and 54 degrees that we see on our cool vapor line is about 30 degrees of superheat. So we know that the indoor coil in this example is 30 degrees of superheat, and that coil is starved for whatever reason. And subcooling. Let's review subcooling one more time before we get into diagnostics. Subcooling always applies to the warm coil. And if the subcooling is high, that coil is flooded. If the subcooling is low, the warm coil is starved. If the subcooling is about 10 to 15 degrees in the cooling mode, we'll consider that normal subcooling. If the subcooling is about 15 to 25 degrees in the heating mode, that will be considered a normal range. Now, to find subcooling or to measure subcooling, we're going to, number 1, convert liquid pressure to temperature off of our pressure temperature chart. Step number 2, we're going to physically measure the liquid line temperature. And then step number 3, we'll find the difference. And the difference is your subcooling level. Now remember, team, if the subcooling is high, a big number, that coil is flooded. If the subcooling is low, that number will be a low number will indicate a starved coil for subcooling. So let's do one more practice before we get into diagnostics this afternoon. At 540 pounds of R410A, we see that at 540 pounds we have a pressure temperature conversion of about 140 degrees, and the temperature leaving on our liquid line from the warm coil is 106. This happens to be in the cooling mode of operation. So the difference between 106 and 140 is about 34 degrees. So the outdoor coil is seeing 34 degrees of subcooling. That coil is flooded for whatever reason. Okay, team, at this time, if you'll please take your handout. or your workbook and find where it says Diagnosing System Problems, heat pump. Now, team, at this time we're going to start doing some service calls, and we're going to encourage you to remember these parameters, and please keep your Diagnosing System Problems sheet and your pressure temperature chart handy as we do some service calls as we round out Module 6. Now, at the very, very bottom of your page, you're going to notice there's going to be some parameters that I'd like you to consider when we're talking about heat pump diagnostics. Number one is if you have a particular factory chart that will give you suction pressure, then by all means use that factory chart. If you have a factory chart available to you on some of our competitors' brands of equipment, and they give you liquid pressure under any given conditions, by all means use that information. However, moving forward on our service calls today, we're going to be looking for a superheat range of about 10 to 15 degrees, and that will be in the cooling mode of operation. The superheat range will be about 10 to 15 degrees in the cooling mode, and in the heating mode of operation, our superheat will run anywhere between about 4 to 15 because we can start icing up that outdoor coil. Now, team, always remember too that if you have low superheat or if you're having issues with airflow on the indoor coil, especially in the cooling mode of operation, that can affect system performance. So always check your airflow, make sure both coils are clean, your outdoor coil and your indoor coil are clean before you do any of these diagnostic procedures, and make sure that airflow is 400 CFM per ton of cooling on that indoor coil in the cooling mode. Now, subcooling today, we're going to be looking for about 10 to 14 or 10 to 16 degrees, depending on the SEER rating. But if you can please remember subcooling in the cooling mode about 10 to 15 in the cooling mode. And in the heating mode of operation, we want to see about 15 to 25 in the heating mode of operation. Now, as we continue looking at our parameters right now, team, remember maximum temperature drop we're going to allow on the liquid line will be 8 degrees as we take a look at our diagnostic screens today. Maximum temperature drop we're going to allow on any suction line in the cooling mode of operation or in the heating mode of operation, that cold suction line leaving the cold coil should not exceed 3 degrees. In addition, the maximum temperature drop allowed on any filter dryer, any of our bi-flow filter dryers, will be a 3-degree temperature drop. Any more than 3 degrees, we know we have a restricted dryer. So that'll be a key point when we do our service calls here shortly, that if we have a big temperature drop or a big temperature difference across the two cool lines of the reversing valve, we know we have a problem. We know if we have a big temperature drop across a liquid filter dryer, that dryer's got a problem. So be looking carefully for temperature differences across filter dryers and the liquid line itself and the suction line and the reversing valve. These are all important key things. Now let's take a look at that diagnosing system problems a little bit closer in some of the service calls. We see, for instance, if we have a low heat load in the upper left-hand column right there, if we have a low heat load, in other words, we're not getting the proper airflow across the cold coil, it's going to drive the superheat low. We'll also observe low subcooling and low suction pressure and low discharge pressure if we have low airflow on the cold coil. Now, team, remember that can be the coil outside in the heating mode is the cold coil, and the coil inside is in the cooling mode of operation is the cold coil. So remember, if we have low airflow across the cold coil, it doesn't matter if it's outside or inside, it doesn't matter what the mode of operation is. We find the cold coil. If it has a low heat load on it, in other words, we don't have proper airflow on that coil, maybe the outdoor coil is icing up in the wintertime, that's going to drive the superheat low, the subcooling low, the suction pressure low, the discharge pressure low. If we have a dirty air filter in the cooling mode of operation, we have a dirty air filter inside the home, it's going to have low airflow on that cold coil, and it's going to drive the superheat low, the subcooling low, the suction pressure low. You get the idea, everything will go low. So as we take a look at these service calls today, please be sure and have your diagnosing system problems page handy so that we can do these service calls together and you can follow along and see how we can diagnose system related problems just by looking at pressures and temperatures and superheat and subcooling. Let's do another one. Let's say we have a low refrigerant charge. What will that look like? Well, if we have a low refrigerant charge, we'll see that we'll have high superheat, low subcooling, low suction pressure, and low discharge pressure, and so on. So as we take a look at these service calls we're going to be doing next together, remember, team, just watch, look at your pressure temperature chart and watch your diagnosing system problems page and pay close attention. And we'll do some service calls to kind of get you warmed up and looking at refrigeration cycle on a heat pump. And by all means, use this recorded session to go over these sessions over and over again until you're comfortable with diagnostics. And by all means, please call me or call my team members if you have questions. So let's do some service calls together. The first thing that we notice on this service call is we've got a R22 service call. We have 42 pounds of suction pressure, 297 pounds of discharge pressure. You'll also notice that we've activated all the yellow temperature blocks. We have also indicated a green temperature block near the outdoor coil, and that's our outdoor air temperature. In this example, it's 87 degrees outside. We also have activated a green temperature block near the indoor coil. Now, we are in the cooling mode of operation. The outdoor coil is warm, the indoor coil is cold, and we see that we have an indoor return air temperature of 63 degree wet bulb temperature. So these two temperature blocks tells us the actual temperature of the air passing over those coils. 87 degrees outside, 63 degree inside. As we take a look at the refrigeration cycle, we see that all of the temperature blocks have been activated. We see we've got 54 degrees across the indoor coil vapor line, and we have a 2 degree temperature rise across the reversing valve from 54 to 56, which is normal. That's fine. We also see that we have a liquid line temperature of about 75 to 74 degrees. And we see we have 88 degrees leaving the outdoor coil. So we've activated all of the temperature blocks. Now, team, remember we talked about we should never have any more than a 1 or 2 degree temperature difference across any key component like a biflow filter dryer. Now, as we take a look at this refrigerant screen, we see our suction pressure is actually low that we'd expect on a R22 call in the cooling mode of operation. We also notice that our discharge pressure is somewhat elevated. Well, if we take the superheat on the indoor coil, which is cold, we see at 42 pounds of suction pressure for R22, we're running approximately 19 degrees of pressure temperature conversion at 42 pounds of pressure. However, 19 degrees compared to a 54 degree indoor coil vapor suction line temperature, we see that we have over 30 degrees of superheat. So the indoor coil in this example is starved. We have high superheat. We also have low suction pressure. We also have high discharge pressure and elevated subcooling levels. So as we take a look at our diagnosing system problems, you see that you have low suction, high discharge or liquid line pressure, superheat is high, and we have an elevated or high subcooling. And so if we look at that closely, we know we have a liquid circuit restriction of some kind. So we can narrow our focus down now to the liquid side of the system. Well, the liquid line, we see we have a 1 degree temperature drop, our 1 degree temperature difference between across the liquid line with our two temperature blocks, 74 and 75. We see that we have no temperature difference between the biflow filter dryer. They're both 74 degrees. But now hang on a second. Look at the temperature difference leaving the outdoor coil and entering the biflow dryer. We see that we have 88 degrees and 74 degrees. Now remember, team, the biflow TXV has a check valve in it that's supposed to allow liquid to flow freely in the particular mode of operation that it's in. So in this example, the outdoor TXV should be flowing freely in the cooling mode and metering refrigerant into the outdoor coil in the heating mode. Likewise, the biflow TXV on the indoor coil should meter refrigerant into the indoor coil in the cooling mode, but flow freely through its check valve circuit in the heating mode. Well, we see that the biflow TXV outside, which should be flowing freely in the cooling mode, has got a 14 degree temperature difference across that biflow TXV check valve circuit. So we can reach the conclusion then, we know we have a liquid circuit restriction with low suction pressure, high discharge pressure, elevated or high subcooling, and high superheat means a liquid circuit restriction. And as we start taking temperatures across the liquid line components, we see we have a 14-degree temperature drop across the biflow TXV outside that should be flowing freely through its check valve circuit. And we should have no temperature difference, maybe 1 degree maximum, but no temperature difference, no significant temperature difference. So we have a 14 degrees. So our diagnosis in this one is we have a liquid circuit restriction. The outdoor TXV check valve circuit is restricted. And there we go, restricted outdoor TXV check circuit. Let's do another service call. In this example, we see we have an R22 call, and it's 94 pounds of suction pressure. Now, it is a hot day outside. It's 101 degrees outside with a 67-degree indoor wet bulb. So as we take a look at this service call together, we see that we have a 94-pound suction pressure, which is pretty high for an R22 system. But let's go ahead and take a look a little bit deeper and look at our superheat and subcooling as well. So at 94 pounds of suction pressure, we see that we have a 56-degree pressure temperature conversion on the suction side. So at 56 degrees, we notice that the indoor coil has got about an 18-degree superheat, 18 to 20 degree superheat. Now remember, team, we need about 10 to 15. So the superheat is elevated on the indoor coil. So the superheat is elevated. That means that coil is starved to slightly starved. Let's keep working. At 325 pounds of pressure, for R22, we see that we have a pressure temperature conversion of about 138. And the temperature leaving on the liquid line of the outdoor coil in the cooling mode is 127. So we have a subcooling level of 11 degrees. That's normal. So we have high superheat, about normal subcooling, high suction pressure, and high discharge pressure, or liquid pressure. So referring to your diagnosing system problems page, let's find a condition that will give us high suction pressure, high discharge or liquid pressure, about normal subcooling, and high superheat. You'll find that the answer is a high heat load on the cold coil. And that's correct. If you have high heat energy, if you have a lot of heat energy hitting the indoor coil, or in this example, the cold coil, it's going to drive both pressures up, the superheat up. But if the unit is normally charged, if it has a normal charge, the subcooling will be about normal. In this next example, we see we have an R410A service call. Our suction pressure is 88 pounds of pressure, which is low for an R410A unit. Discharge pressure is elevated. It should be running about 360 or so, or maybe 375. However, it's elevated. So our suction pressure is low. Our liquid pressure is high. And if we do our superheat on the indoor coil, let's do that together. At 88 pounds of suction pressure, we see that we have a pressure temperature conversion of about 25 degrees, but the temperature leaving on the cold vapor line from the indoor coil is 69. So the difference between 25 and 69 is about 45 degree superheat. So our suction pressure is low, liquid pressure is high, subcooling is elevated, superheat is high. So what would give us low suction and high superheat? That's the key. Well, team, if you found on your diagnosing system problems another liquid circuit restriction, that is correct. But let's narrow that down some. So as we take a look at the temperatures across the liquid line circuits, we have 102 degrees across the biflow TXV. That's normal. That's fine. We have 102 degrees across the biflow TXV outdoor and the biflow filter dryer. So there's nothing wrong with those components. But now hang on a second. Look at the difference between the outlet of the biflow dryer and the other end of the liquid line entering the biflow TXV inside. We have 102 degrees and 74 degrees. So we should never have any more than about 6 or 8 degree temperature difference across that liquid line. However, In this example, we've got about 26 to 27 degree temperature difference. So in this example, we see we have a restricted liquid line. It could be a kink, it could be an undersized line, it could be a fitting that's been filled up with solder, our braze material. So in this example, we have a restricted liquid line that we'd have to address and find out why and correct. So a restricted liquid line. And the big thing that we found, team, was a low suction pressure, high superheat on the cold coil, and a big temperature drop across that liquid line. Let's do another example here. Here we have a 410A unit with 148 pounds of suction pressure. As we take a look at our pressure temperature chart at 148 pounds of pressure, that gives us about approximately 53 degrees at 148 pounds of suction pressure. So we take a look at our cool vapor line, our indoor coil vapor line, and we see that we've got 62 degrees. Well, the difference between 52 and 62, or 53 and 62, is about 9 to 10 degrees of superheat. So the indoor coil is normal in this service call. Let's take a look at the subcooling on the warm coil. As we take a look at our pressure temperature conversion for R410A at 503 pounds of pressure, we see that gives us a pressure temperature conversion of about 134 to 135 degrees. As we take a look at the temperature leaving the warm outdoor coil in this example, we see we have 104 degree liquid line temperature. Well, we have a pressure temperature conversion off the discharge gauge of 503 pounds of pressure is equal to 134 degrees. So we have 30 degrees of subcooling on the outdoor coil. Now remember, team, in the cooling mode of operation, the outdoor coil should have a subcooling level of about 10 to 15, but we have 30. So the outdoor coil is jam-packed full of liquid. The indoor coil is about normal. Suction pressure is slightly high, but not too bad, and we have high discharge pressure. So normal suction, normal superheat, high discharge pressure, high subcooling. This is a classic overcharge with an operating and functioning expansion valve. So suction pressure is about normal, superheat's about normal, but our discharge pressure is high and our subcooling is very high. So the indoor TXV is operating properly. It's throttling the refrigerant like it should. But remember, team, with a system that's equipped with a TXV, we always use subcooling as our method of charging. And so in our example here, we see we have a gross overcharge with 30 degrees of subcooling on the outdoor coil in the cooling mode and about normal superheat because our expansion valve on the indoor coil is working properly. This is an overcharge with an operating TXV. Okay, team, on this one here, we see that we've got 117 pounds of suction pressure. It's an R22 call. And at 117 pounds of suction pressure, we've got a pressure temperature conversion of 68 degrees. So 68 degrees, we see that our superheat is way out of calibration. It's actually ranging, if you take a look at our cool vapor line, anywhere between 2 and 14 degrees across that reversing valve. Now remember, team, one of the big things that we always want to look for, whether it's an R22, R4, or a 410A system, is when we take a look at the reversing valve, if we've got high suction pressure and low discharge or liquid pressure, which we have in this case here, our pressures are way out of whack. And so at 117 pounds of suction pressure, which is very high for an R22 system, and 188 pounds of pressure is actually low for an R22 system, the first thing that we always want to check is that we want to look at the temperature across the reversing valve, the two cool lines of the reversing valve. Now, we talked about that earlier in our previous modules as far as reversing valve and what the temperature should be across that reversing valve. and we should never exceed about 4 to 7 degrees across a reversing valve. But in our example here, we've got a 12-degree temperature drop, a 12-degree temperature difference between the two cool lines of the reversing valve, coupled with high suction pressure. So anytime you have high suction pressure and a big temperature difference across the two blue or the two cool lines of the reversing valve, we know that reversing valve is leaking and it needs to be replaced. And sure enough, that's our diagnosis. As you take a look at the screen, a leaking reversing valve with high suction and low discharge pressure and a large temperature difference across the two cool lines. Well, team, at this time, let's continue with some service calls. In this service call here, it's an R410A system. We're in the cooling mode of operation. We have 136 pounds of suction pressure. At 136 pounds of suction pressure for a 410A unit, we see that we've got a pressure temperature conversion of about 47 degrees. Excuse me. And our temperature on the vapor line leaving the cold coil is 57. So in this example, our superheat is about normal. As we take a look at our discharge pressure, 360 pounds of pressure, we see that we have a pressure temperature conversion of about 111 degrees and at 360 pounds of pressure, and the temperature of the liquid line leaving the warm outdoor coil in the cooling mode of operation is 99 degrees. And so at that particular point, we're looking at approximately 11 to 12 degrees of subcooling, which is normal. So the suction pressure is normal. Liquid pressure is about normal. Subcooling is normal. Superheat is about normal. As we take a look at the temperatures throughout the refrigeration circuit, we see that they all, there's no significant temperature difference across key components in the refrigeration circuit. Pressures are normal. Superheat is normal. Subcooling is normal. This is a normal service call. And team, this is important that we recognize normal as well when we're doing diagnostics. We need to be able to recognize normal as well. Okay, team, and on this particular one, we see that we have an R410A call, and we have 114 pounds of suction pressure and 292 pounds of discharge pressure. So at this time, please work out, we'll give you a little bit of time, please work out the pressure and the temperature conversion for the suction line as well as the discharge line, discharge pressure. And so let's find our subcooling, let's find our superheat, let's find our pressures and temperatures and look at all the temperatures throughout the refrigeration circuit, and let's see if we can diagnose what's going on. So I'll give you a little bit of time to do this as we move forward with some of this interactive service calls. We want to look at our pressures and temperatures. I'd like you to work out your superheat and your subcooling. Look at all the temperatures throughout the refrigeration circuit as we pick the pace up a little bit. In our example here, we see our suction pressure is a little bit low. We also see that our superheat is low. And if you're working on your subcooling, you'll find your subcooling is a little low. And discharge pressure is low. So look at your superheat, subcooling, pressures, and temperatures. And let's work this out together. So suction pressure is low, liquid pressure is low, superheat is low, subcooling is low. What's your diagnosis? Good, whoever said low heat load. If we have a low heat load on the cold coil, in other words, if we have inadequate airflow on the cold coil for whatever reason, it's going to drive the suction pressure low, the liquid pressure low, the superheat low, and the subcooling low. Okay, team, at this time, let's take a look at this service call. It's a 410A service call. I'd like everybody to make a real good look. We see that we've got low suction pressure. And please notice all the temperature probes around the refrigeration circuit. Look at those closely. And in this example, we see that we've got a restricted outdoor check valve again on our outdoor TXV. We're in the cooling mode of operation, and we have a large temperature difference, a 19-degree temperature difference across our BiFlow TXV outside. But we also notice our suction pressure is low, our superheat's high, our subcooling is elevated, and our discharge pressure is high. Liquid circuit restriction, and we find that by taking accurate temperatures across the liquid line components. Okay, team, let's do another one here. We have 102 pounds of suction pressure for a 410A unit. We have 293 pounds of discharge pressure. It's 92 degrees outside. This 410A unit is in the cooling mode of operation. Our suction pressure is low, our discharge pressure is low. Our superheat is high. Our subcooling is low. So both coils are starved. We have low subcooling. We have high superheat, low subcooling, and both pressures are low. This is a classic low heat, low charge. This is a low charge. Okay, on this one here, team, let's take a look at this closely. We see we have 89 pounds of suction pressure, 388 pounds of discharge pressure. We have high superheat. We have high subcooling. So we know we have a liquid circuit restriction of some kind. As we take a look at all the liquid line components, we see no problem on the liquid line components. So by a process of elimination, if we know we have a liquid line restriction or a liquid circuit restriction, but all the temperatures look okay, then we conclude that we have a restricted indoor TXV in this example. Let's switch modes of operation real quick. We see we have a 410A unit in the heating mode of operation. And as we take a look at our components, as we take a look at the temperatures across our components, remember, team, even though it's in the heating mode of operation, the refrigeration cycle still applies. We see we have quite low suction pressure, high discharge pressure. Temperatures across the two cool lines of the reversing valve are normal. The liquid line temperature leaving the warm indoor coil is 77 degrees. But hang on a second, look at that. We've got a 15-degree temperature drop across, a 25-degree temperature drop across our BiFlow filter dryer. Large temperature drop across our filter dryer. And so we know we have a restricted filter dryer in this example. So remember, team, temperatures are extremely critical as you look through a refrigeration cycle. And it should be noted, too, that everywhere there's a yellow temperature block, this is where we recommend technicians, when we're coaching our contractors and coaching our technicians, to be sure and take a lot of really accurate temperatures around the refrigeration circuit. It'll help them be better troubleshooters. In this example here, we have another 410A system. And as we take a look at it, we see it's in the heating mode of operation. Across the two cool lines of the reversing valve, we see that's about normal. We only have about a 1 degree difference. We see the BiFlow TXV on the indoor coil in the heating mode of operation should be flowing freely. And we've got about a 1 degree temperature difference across there. That's normal. But now, team, on this particular service call, you'll notice we have low suction pressure, and we also have a very large temperature drop across the liquid line in this case. So in this example here, we've picked up on this. Maybe somebody was in the attic and they stepped on the liquid line when they were up there doing a service call or cleaning the coil or whatnot, if it happened to be in the attic. And we see that we've got a huge temperature difference now across the liquid line, and we have a restricted liquid line. Now remember, team, it doesn't matter if you're in the heating or the cooling mode of operation. Any temperature difference, any more than about 6 to 8 degrees across the liquid line, you know you've got a restriction in it. So here we have a restricted liquid line as our diagnosis. Okay, in this example here, we have a 410A unit. We are, again, in the heating mode of operation. Let's work this one out together. Step by step, we'll do the entire thing. As it looks right now, it looks like the temperatures are all looking pretty good, but let's go ahead and work this out together. So in this example, we have 76 pounds of suction pressure on a 410A unit, and that's about 18 degrees. About 18 degrees. Saturation pressure temperature conversion, so 76 pounds of pressure for 410A is about 18 degrees. The temperature leaving on the cool or the cold outdoor coil is 39. So we have a 21 degree superheat, 21 degrees superheat on the outdoor coil. So let's keep working at 269 pounds of pressure on the discharge line for 410A. At 269 pounds of pressure, we have about a 89 degree pressure temperature conversion, and we have 87 degrees leaving the warm indoor coil. So let's convert that. We see that our subcooling is very, very low on the indoor coil. It's acting like a condenser, so that coil is starved or empty. We see that we have high superheat on the outdoor cold coil, and the outdoor coil superheat was 21 degrees. That's very, very high. It should be anywhere between about 4 or 5 as high as 15 based on the temperature outside. But we see we have 21 degree superheat, so the outdoor coil is starved. We've got 2 degrees of subcooling on the indoor coil. The indoor coil is starved. Suction pressure is low. Discharge pressure is low. All the temperatures around the refrigeration circuit, as far as the liquid line and so on, that all looks fine. There's nothing jumping out as far as a kinked liquid line or anything like that. But what condition, let me ask everyone, what condition would give us high superheat, starved outdoor coil, low subcooling, starved indoor coil in the heating mode, low suction pressure and low discharge pressure? In other words, 2 starved coils and both pressures are low. How about a low charge that we just happen to pick up in the heating mode of operation? Low charge, classic low charge, 2 starved coils, and both pressures are low. Okay, team, in this example here, we have a 410A unit, and it's in the heating mode of operation. As we take a look at the refrigeration circuit and the pressures, we see that we have really low suction pressure for a 410A unit. And being in the heating mode of operation, we have considerably higher discharge pressure as well. So as we work this system through and we take a look at it, we notice that something that really jumps out at us is the indoor bi-flow TXV. Now here's the service call. The homeowner said it worked fine in the cooling mode. But in the heating mode of operation, we see the suction pressure drop down significantly, and we're supposed to be flowing freely on that indoor TXV, but we see that the check valve circuit is restricted, and we have a big temperature drop across that bi-flow TXV on the indoor coil that should be flowing freely. So in this example here, we have an indoor TXV restricted check valve circuit. Team, at this time, we're going to go ahead and conclude our Module 6. We want to thank you very much for your attendance today. And, of course, if this was a live session, we'd be taking any final questions or comments at this time. But because it's a recorded-only session, we're just going to thank you so much for your attendance and your listening to the recording today. I encourage you to please go back and look at all the service calls and work them out and take some time to really digest those service calls. And by all means, if you have any questions or comments, please contact myself or any of my team members on the Champion team. And on behalf of your Champion team, we want to thank you again so much for your attendance and listening to this recording today. Thank you, and be safe.